Temperature dependency, what do you think will happen to the speed of a chemical reaction when you increase the temperature?
It would increase.
It will increase, definitely. It has been found out that this is like the same across.
But
We will come to that. So we're talking about temperature dependency. As temperature increases, the rate also increases. And we'll be going through the mathematical significance of this. Yeah, Sia, what's up?
Won't it be different for exothermic and endothermic?
That's a very good point. Even Kaveri had that doubt earlier. So what you must be thinking of is when it comes to exothermic, endothermic, is the equilibrium shifting forward or backward. Okay. So think about it. So for this, okay, the formula will do it later. But pehle, how do you think chemical reactions take place? Like, क्या होता है chemical reactions में? Let's go back.
Molecules collide.
Yeah. And what happens when molecules collide?
Reaction.
So when molecules collide, some bonds are broken, new bonds are formed. When new bonds are formed, the atoms are basically rearranged into different molecules, which is what we call as the products, new substance being formed. Okay. So in order for this to happen, in order for bonds to break or new bonds to be formed, you need the molecules to collide with each other. And not just that, they need to collide with each other in a very specific way. The best example I can think of, what you're familiar with, is the Sn2 reactions. So Sn2 may, you have the nucleophile colliding against it with the haloalkane, like in a very specific way, behind the leaving group. Like agar leaving group ka bond idhar hai, so it needs to collide from this. If you have another nucleophile which is approaching it from this direction, there is going to be no reaction. It needs to happen in a very specific way. Like once this collides, approaches it from backside, then yeah, this bond starts to break, this bond starts to form, and then reaction ke baad you finally have the same thing, new product and X minus, like basically different products. Bonds are rearranged, right? So keep this in mind that molecules need to collide, and in order for the molecules to collide, you need, like, they need to move in order to collide. If they're not moving very well, if you know, think of a block of ice or a crystal, they're just there. They're moving slightly, but like in their positions only. Now that's not going to help with the chemical reaction at all. Now, what does increasing temperature do?
Causes the molecules to move faster, like they gain more energy.
Correct. That's something we have done in thermodynamics, right? Increasing the temperature, matlab, you are basically increasing the internal energy of the molecules. Internal energy, nothing but the kinetic energy that the molecules have. Molecules move faster, matlab, we are just increasing the chances for them to collide against each other a lot more. So that is why always when temperature increases, rate of a reaction also increases, compulsory. Now coming to your doubt, let's take a reaction. A plus B gives C plus D. Let's say it's a reversible reaction, which means once you have certain amount of CD, when these two collide, you'll get some amount of A and B back. Now, this whole reaction is taking place in a single vessel, container, whatever, A, B, C, D, all of them are in over here only. When you're increasing the temperature of this system, you're increasing the rate of A and B shear, inka speed, like speed of the molecules, kinetic energy of these molecules is increasing, more collisions happen, reaction happens faster. But at the same time, CD are also there in the same vessel, which means you're increasing the kinetic energy of CD also, which means these guys also will collide, and then the speed of the backward reaction also will increase. So in that sort of a situation, then you look at whether it's exothermic or endothermic, and then you can figure out which out of the two is going to dominate. So that decides the shift of the equilibrium. But if you're considering only the rate of the reaction, reactions will always get faster. When you increase the temperature, reactions will always get faster. So exo-endo comes into picture when you also have a backward reaction and you're looking at the shift in the equilibrium, because you're equally increasing dono ka speed by the same rate.
So for a normal reaction which can't move backwards, then it increases with temperature.
Yeah. Any reaction will
but-
increase. So rate of a reaction will always increase. It's just the extent kitna product milega that will be decided by exo-endo. Rate will always increase. No case, no question, nothing else to be taken into consideration. So rate of a reaction will always increase. Rate always increases. Now, equilibrium, whether you're going to have the forward reaction or the backward reaction, will depend on whether one particular direction is exo or endo. So if it is exothermic, then it will favor the backward reaction while speeding it up. Like rate will always increase.
Miss, what do you mean by favor then if it's not increasing? I mean, the rate is increasing. So is that what we mean by favor or?
No. Favoring means that side of the reaction will dominate. So you'll get less of C and D because they're reacting back to give you A and B. Like the equilibrium, see, once equilibrium is established, forward is equal to backward, right? Like you won't get products, like concentrations are not going to change. So at that point, you may find something like only 15% of the products have been yielded, and then 85% is still the reactant.
But then how is that possible if the forward reaction is equal to the backward reaction?
Forward reaction equal to backward का मतलब concentrations equal नहीं है. It's just the rate of the forward reactions is equal to rate of the backward reaction. So if the forward reaction is slow compared to the backward reaction, if no conditions are more suitable for the backward reaction, then like let's say 10 or okay, like what dynamic should I use? So yeah, if the backward reaction is a lot fast, as soon as a molecule of C is produced, it's going to react with a molecule of T. That might not be the case with A and B. Like even though you have 85% of the concentration is still consisting of A and B, they're not reacting with each other.
But that still means that the C and D reaction is much faster because it's happening immediately. Whereas if A and B are not reacting that quickly, मतलब उनको ज़्यादा time लग रहा है. So then how does it mean that the rates are the same?
No, rates will be equal. So it's not to do with the, see, rate of the reaction is how much of the concentration is changing per unit time.
Can you say that again?
Yeah,
The rate of the reaction means
the change in concentration like per unit time. Right, like how much of this is reacting in 1 second, how much of this is reacting in 1 second, that way.
So what I understood till now is when you have a reaction that is not like reversible, in that case when you increase the temperature, reaction will happen faster. In case of equilibrium also it will happen faster only, which means कि पहले अगर rate if the forward reaction rate is X and backward reaction since its equilibrium is X only, but then if you increase the temperature, both will become 2X.
Yeah.
But like, right? But the only case where when we talk about, like Sia said, exothermic or endothermic, in that case, we're talking with respect to whether more product is formed or whether more of the like less product is formed, basically.
Absolutely correct. Equilibrium will only tell you the relative concentration of the reactants and products. Correct.
So,
Can
but
you go
then
to
what does, sorry, one second. When we say that equilibrium shifts towards this, like one side, as in more product is formed, like, so that's why equilibrium is shifting towards the product side. That's what.
Yeah, like at one temperature, let's say, or like in condition 1, you would have 85-15. When you change the condition, if we are saying that equilibrium shifts to the right, you end up
Yeah.
getting something like 60-40 maybe. So it is favoring the formation.
But the rate is still the same.
Rate may, I mean, rate of forward will be equal to rate of backward. Yes.
Yeah.
Yeah, correct.
Thank you.
Okay. Yeah. See how you were going to ask what's your question?
No, could you go to the previous page?
I mean, there's nothing to note down yet. I'll tell you, like, the main thing is that when temperature increases, the rate of the reaction also increases. Whatever we discussed now, we'll be putting it like collision theory, that's what is there. And then we'll also look at the numerical formula that Arrhenius proposed for this.
Miss, have you, like, is there a recording of this crystal field theory that you did with Smera, like the first one that you?
There should be, yeah.
Yeah.
I need to go through it because I have a feeling I uploaded the coordinate compounds ka thing twice. There's like too many videos of it. But yeah, there definitely is.
Ma'am, about the test that we just had, like we had for coordination chemical kinetics, I could solve for chemical kinetics and coordination, I could do the nomenclature because you had done that properly with us. But anything before that, I was not able to do it. Like it was, I think it went over my head.
Crystal field and all of that.
Yeah.
Okay. Cool. We'll do that. Okay. All right. So yeah, now we're getting to the meat of this thing. So first thing is Arrhenius equation. So the spelling always trips me up. Arrhenius. So he, by studying a lot of things, by doing a lot of experiments, doing the analysis, seeing the variations, he came up with this relation with temperature. So he, 2 points to it. He found out that for every 10-degree rise in temperature, 10 degrees rise in temperature, 10 degrees.
Can you wait for 2 minutes, please? I want to write down what you said about equilibrium. Then I'll forget.
Yeah. Should I switch to the previous slide or something?
Yeah, please.
I don't know what you'd get from this, but
not. I think Sia wants the previous one. There's nothing in this you can.
No, I finished.
okay. Let me know when you're ready to resume. Huh? Okay, cool. So qualitatively, we've discussed that, okay, as temperature increases, rate of a reaction increases. The next step is to find out the relation between them. Like generally, it's been observed that for every 10 degrees rise in temperature, Celsius, Kelvin, the same thing, because you're looking at change in temperature, the rate of the reaction is doubled. This is the thing found out. So Arrhenius was the one who finally gave a relation between both. So his equation, he he actually found out and he postulated that K is equal to A into E power minus EA by RT. So in which K, do you guys know what K is?
Rate constant.
Rate constant. So this is where the temperature dependency of K comes from, and it's because K changes that the rate of the reaction changes. Okay, this is where it's there. A is a number. This is called Arrhenius factor or frequency factor. So frequency factor relates to the frequency of collisions, you can say. So like that's kind of what it relates to. Next we have EA. This is the activation energy for the reaction. And R is your universal gas constant. And T is temperature in Kelvin. Always in Kelvin in these calculations. Okay. So you guys don't have like numerical applications based on this formula. You just need to know this formula and this particular relation. Just know that Arrhenius equation exists. Yeah.
What is Arrhenius factor? Like, is it like one constant or is it like
It
they'll
is
give it
a,
in the
yeah.
question?
No, it is a constant. It is a constant for a particular, it's not a universal constant. It's constant for a particular uh, reacting species, for a particular reaction. And it relates to the number of collisions, like frequency of collisions that occurs.
So like he said that for any reaction 10-degree rise made rate is doubled.
Yeah. So you plug the values. So like usually, like whenever this changes by 10, the rate of the reaction happens to be doubled.
So like this is matlab valid theory or like
This is like generally it's been found out. This is more of a, it's like precursor to what Arrhenius proposed. They were like trying to find out, okay, temperature increases, rate increases. Let's see what is the relation. Is it a straight line? Is it logarithmic? Like, kya ho raha hai yahan pe? And they found out
no
that
like
10 degrees mein
oh,
it's being doubled.
so like this is true. Like if we had to calculate this now, every 10-degree rise in temperature, we would see that the rate like the reaction is faster by 2
Yeah.
times.
Yeah. Okay. So rate constant, yes, we've studied about it. Arrhenius factor is like a specific constant related to a particular reaction, changes with different reacting species. Activation energy, you guys know what activation energy is?
We have learned it for enzymes in
Oh,
bio.
okay.
Yeah, we did it in bio.
Okay. Smeha, what about you? Any idea what activation energy is?
Never come across.
Never come across it? Okay. Uh, Simply speaking, activation energy is the energy required to activate a reaction. So, candle burns, right? What is the candle burning or oil burning wala reaction? Or even a matchstick burning, like what is that burning wala reaction? What happens in that reaction? Which are the reacting species?
Carbon dioxide is produced.
From
As far as that, I don't.
is what? Like, guys, this is 7th standard stuff. What happens in combustion reactions? What do you mean by burning?
Oh, oxygen is required.
Yeah.
Yes.
That,
So if I'm burning, let's say, let's keep things simple, paper. Why is oxygen required there? Like, what is that reaction between? Okay.
does it have to do with the constituents of the thing? No, it doesn't.
Yes. Why no?
Constituents of the matchbox or matchstick or something.
Yes.
But I don't know what is there in it.
That's phosphorus, right?
Phosphorus or phosphorus related compounds. Yes. Okay. So that reacts with oxygen, produces a lot of energy. That is what burning is. It's hydrocarbons, even wax, oil, all of these are hydrocarbons. They're organic compounds. We're studying about it, paraffins, stuff like that. So combustion is hydrocarbons reacting with oxygen, producing carbon dioxide, water vapor. But oxygen is in atmosphere, it is available. But how come your matchstick, paper, candle, they're not burning automatically? Yeah, cute. You need to, like give that initial spark, right? Like matchstick ke case mein, you're what do you like doing this against that box? You're giving it friction.
Friction, right?
And in the case of paper burning, you're bringing a flame near it, like a burnt matchstick or an existing flame. Even for candle, you're bringing an existing flame close to it in order to kickstart that reaction. So what you're doing by doing all of these actions, by increasing the friction or by bringing the flame close by, is you're giving that activation energy to those reactions so that they can happen and continue on their own. Okay. So whenever you like, so this, along with this comes a graph. So when a reaction happens, there's like two reacting species involved. So if you measure the potential energy, like before a reaction happens, while the reaction happens, and after it happens, the graph kind of looks like it. So before the reaction happens, they'll be at a certain level. Once you kickstart the reaction, like if you want the reaction to happen, energy first increases and then it decreases. So decreases, it can be anywhere. Usually it's like till here. So this difference, yahan se yahan tak, this difference in energy that is required so that, the reacting species can, metaphorically get over the hill and then become products. So this difference in energy is called activation energy. So what happens is, so like you guys have observed this during organic reactions whenever we do the mechanisms, right? So suppose we have A plus B reacting. So they form like some sort of an intermediate in between, which is pretty unstable. So it could be like OH2 in the case of alcohols, or SN2 reactions mates, that 5 bonds wala species. Like beach mein you have this where the nucleophile and the leaving group, both of them are bonded, right? So this is very, very unstable because carbon cannot take a valency of 5. So these sort of unstable intermediates are high in energy. High energy, that's why they're like pretty unstable. And then they rearrange to form your products. So which would be again of lower, it can be either lower than the reactant energy or higher than the reactant energy, but definitely less than the activation energy. So this difference in energy, initial minus final, this difference in enthalpy is your enthalpy of the reaction. So if it goes lower, you end up with an exothermic reaction. If it goes higher, you end up with an endothermic reaction. So write down the concepts and then we'll do the graphs for both exothermic and endothermic. So this difference is activation energy. The highest point, this energy is called threshold energy. Like you need to cross that threshold in order to get the products. If you don't cross this threshold, you will not get to the products. So this is
So that's another name for activation energy.
no, activation energy is the energy required for activating. It's the difference. This absolute numerical value jo hai, 0 to like whatever this value, that is threshold energy. Activation is yahan se yahan tak, this difference, because they are already, like the reactants already are at certain energy level. So nikal ke this difference is activation. This point on this graph, this is the threshold energy.
What did you say about the graph decreasing? You said some reasoning.
Unstable hai, so like increase in potential energy. And then once the products are formed, they become stable again. So the energy.
So like, can you this graph is, can you like write x-axis?
Huh,
Yeah.
yes, will do. I was just talking about it. So x-axis, this is the potential energy. And this is the extent of the reaction. So this is when it is individual A plus B. This is when it's the unstable intermediate, and this is when the products are formed, C plus D.
Will we be asked to like draw graphs like this graph?
You may be asked specific cases. What does it look like for an exothermic? What does it look like for an endothermic? Or you may be asked to identify whether this reaction is exo or endo.
What
One
about like
in theoretical?
Sorry. In the pehle wale ones also we did for first order, second order. Those graphs will we be asked to draw?
You may. The probability is very low. If it comes, it'll come most. Like you won't be asked to explain and describe the whole thing. It's going to be a 1-mark question, like identify this, or a graph drawn for a first order is straight line. So what would it be between? Then you should know that it's logarithm versus concentration rather than just
Time, no?
Logarithm of the concentration versus time rather than just concentration versus time. So that sort of a thing.
Yeah. Okay.
Yeah,
but like the
so if you're asked graph-based questions, it's going to be 1 mark.
Okay. And like kya bolte usko? Derivation will be asked, right? Like integration and
If you're asked derivation, it will usually be in combination with the numerical problem, like for 5 marks or 3 marks or something like that. So this difference is delta H. Yahan se yahan tak is activation energy ये. This numerical value y-axis पे जो है, this is the threshold energy. These are your reaction coordinates. Yeah, what else is required? That's basically it. Okay, so at a macro level, threshold energy is the minimum energy, like it's like, okay, potential energy of the reacting this thing. But if at a molecular level, if you have to understand threshold energy kya hai, kitna hai, you can think of it as the kinetic energy required by the molecules so that the reaction can happen when they collide. Like if they're just, if the internal energy, like the kinetic energy of the individual molecules is less, they're just like coming close, very close together, they might just, come close and then go off without reacting. But once they reach the threshold energy, if it is threshold energy or greater, then the reaction will happen when they collide. Otherwise, they'll simply collide and go their way. That's it. So that's like the
But-
minimum energy required so that the colliding molecules can react and form the products. Yes, yeah.
But why kinetic energy? Why can't we use potential energy? Because this graph is versus potential energy.
No, individual molecule में क्या होता है? They have kinetic energy because they're colliding with a certain velocity, right? So उसका associated kinetic energy.
So threshold energy is the energy that is required to start the reaction.
Yeah. Threshold energy is the energy. So threshold energy is the energy that the molecules need to reach in order to start the reaction. But because they're already at this particular level, you just need to give the difference. So this is activation energy. Jitna chahiye in order so that the molecules can reach the threshold